Okay, now the last topic we're going to talk about in 4.3 is curve sketching. So now that we know what derivatives do for us, can we sketch a nice curve? Now, previously, like in pre-calc, we learned how to sketch curves based on their end behavior, based on where their zeros were, but we couldn't really tell where their minimums, maximums were, inflection points, the intervals of increasing, decreasing. I mean, if we drew the graph by plotting a lot of points, we could, but calculus gives us a lot of better and quicker ways to do this, okay? And you got to put yourself in the mind of a mathematician hundreds of years ago. They didn't have calculators. They didn't have computers to graph these very nice for them. So let's see. The first one, it says f prime of x is greater than 0 for all x not equal to 1. We've got a vertical asymptote at x equals 1. We've got f double prime is greater than 0 when x is greater than 5. Oh, I started looking at the problem below it. F double prime of x is greater than 0 if x is less than 1 or x is greater than 3. F double prime of x is less than 0 if 1 is less than x, which is less than 3. Okay, so from this, we have to pick out some information. Let's see. I'd start here. We have a vertical asymptote at 1. So we gotta remember that. We gotta keep that in mind when drawing the graph. Now let's look at these other pieces. What do these other pieces tell us? The derivative, the slope of the graph, the derivative is greater than 0. If you recall, this was the definition of an increasing interval. You are increasing over an interval if the derivative is greater than 0 on that interval. Now it says it's greater than 0 for all x not equal to 1. That's because we have a vertical asymptote. That means this graph is always increasing. As we go left to right, every tangent we draw on the graph should be positive. Now, if you look at these two conditions, they deal with the second derivative. The second derivative dealt with concavity, okay? Now, the second derivative is greater than 0, okay? If you're greater than 0, again, how I remember it, if you're positive, you're opening upward because that's the positive y direction. So that means we're concave upward on x is less than 1. So let's go ahead and write that. Concave up from negative infinity to 1, union 3 to infinity. So that's what this is saying. The second derivative is greater than 0 when you're less than 1 or you're greater than 3. I guess we could say we're increasing from negative infinity to 1 union 1 to infinity. This one, the second derivative is less than 0 if you're between 1 and 3, so we're concave down from 1 to 3. Alright, so let's get rid of everything. Let's keep the important information. So I'm going to get rid of that. I'm going to get rid of that. I'm going to get rid of this. Okay? And I'm going to rewrite everything. I'm going to put it over here. Got a vertical asymptote, x equals 1. We're increasing from negative infinity to 1, union 1 to infinity. We're concave up from negative infinity to 1, union 3 to infinity. We're concave down from 1 to 3. Alright, now these are rough sketches. They don't have to be perfect. So we've got a There's my vertical asymptote. Now, I'm concave up from negative infinity to 1. So, everywhere here, negative infinity all the way to 1, I'm concave up. So that means I got to draw something that goes like this. Okay. Now, I don't know where it levels off or anything. All I know is it goes something like that. So we're concave up from negative infinity to 1. Not only that, we're increasing. Everywhere along this graph, we are increasing. Okay. So we took care of that. Now we need to be increasing from 1 to infinity. Okay. Now we're concave down. Here's 1. Let's put 3 somewhere over there. Okay. We're concave down, means we got to be down like this. And once we hit 3, we're concave up, but we need to keep increasing. So I'm still increasing, and then when I hit 3, I'm going to go up. See, I'm increasing, still increasing. Keep going, like that. It's kind of like a cubic function. Here, if you look, I'm concave down, and now I'm concave up. Okay, so that's just simple curve sketching from using the derivatives and the second derivatives. Now, you could make a better sketch if you had more information, like if you knew what the function was. You could find the zeros, you could see where this 0 is here, if there is one, or yeah, there's definitely one here. Here, if there's a 0 here, what are the horizontal asymptote on the left side of the graph, if there is one, okay? Now let's go ahead and do the next example. The next example has a lot of information on it. Okay, so it says f prime of 5 is equal to 0. So the derivative is equal to 0 at this point. That means we have a local minimum or local maximum, and 5 is a critical number. That was just definition. Let's see. F prime of x is less than 0 when x is less than 5. So this piece of information, since we got a lot of information, I'll write some of it in red. This one says the derivative is less than 0. We are decreasing when x is less than 5. So negative infinity to 5, we're decreasing. Here we have a local min or max, possibly, okay? Not definitely. Just because the derivative is equal to 0 does not necessarily mean it's a local min or max. It could be. We got to do further testing. All right, what other information do they give us? F prime of x is greater than 0 when x is greater than 5. So it's a lot like this one that we just had. It was decreasing here, so this one says we are increasing on the interval 5 to infinity. Now, we could already determine whether this one is a local minimum or a local maximum by the first derivative test. Okay, think back to what the first derivative test says. It says when the derivative changes from positive to negative on one side of a critical number to the other side, we'll have a local min or max depending on what it changes from. We know that 5 is a critical number. We know when you're less than 5, so on the left side of 5 you're decreasing. On the right side of 5 you're increasing. So it's going to look something like, right there's 5, you're decreasing on the left side of 5, you're increasing on the right side of 5. So from this information right here, I'll write it down here, we have a local min at x is equal to 5, okay? just based off that information so far. But let's go ahead and keep going. Let's continue reading the problem. It says f double prime of 8, of 2, I forgot a piece, of 2 is equal to 0. Let's see, it also says f double prime of 8 is equal to 0. These two right here, the derivative, the second derivative, when it's equal to 0, these are our inflection points. This is where the graph changes from being concave up to concave down, or concave down to concave up. So we're going to need to put these on the graph, okay? So inflection point x is equal to 2 and 8. So I'm going to get rid of some stuff. Everything, actually. Except for our key information. Now we're also told that f double prime of x is less than 0 when x is less than 2 or x is greater than 8. The second derivative is less than 0. Okay? When the second derivative is less than 0, it's negative. Again, how I remember it, it's negative, so it's opening in the negative y direction. This is concave down. So to add more information over here, we know, or right here, we know we're concave down on negative infinity to 2, union 8 to infinity. Here's x is less than 2. Here's x is greater than 8. We have a couple more conditions. Something talking about the second derivative being greater than 0 when x is between 2 and 8. Okay? So that says pretty much the same thing as the top one, except for being concave up. The second derivative is positive. Since it's positive, opening up is in the positive y direction, so we're concave up on 2 to 8. Now we've got two more pieces of information. They're limits. It says the limit as x goes to infinity of f of x is equal to 3. And it also says the limit as x goes to infinity of f of, not infinity here, negative infinity of f of x also equals 3. If you recall what limits going to infinity and negative infinity are, if they go to a finite number, think back to chapter 2. These were the definitions of horizontal asymptotes. Okay, so let me put that over here. Horizontal asymptotes at y is equal to 3. Now, just in this problem, they came out to be the same thing. They don't necessarily have to be the same thing. Okay, now, let's go ahead and write all of our relevant information over here. So, concave down, it was from negative infinity to 2, union 8 to infinity. Concave up was from 2 to 8. All those words and how they were defined by functions, this is the information that you need to extract out of that to draw the graph, okay? So let's go ahead and do this. We've got a horizontal asymptote at 3. So y is equal to 3. Let's see, somewhere on here at 5, we're going to have a local minimum. So somewhere down here, it should look like that. Let's see, over here at 2, we should have an inflection point. So it's going to change from being concave up to concave down, or concave down to concave up. We'll see in a second. And then same thing with 8 over here. Now, we've got our local min done. We've got our horizontal asymptotes done. Now let's see. Let's go ahead and draw this. Now, this graph, what it's going to do, the inflection point is at 8, meaning once we get to 8, so here, let me draw this a little better. At that point 8, it's going to start being concave down. As you see, it's concave down from 8 to infinity. And then when we get up here to 2, or I drew that way too early. When we go to 2, at that point, it goes from being concave up to starting to be concave down. So this is what possibly the graph may look like, okay? Now, we could do a little bit better if we found the, if we had the actual function. We'd be able to find the values of the inflection points and put them there. We'd be able to find the zeros and put them there. So we could do a lot better job graphing it if we had the actual function. But we just have a bunch of details about the function. So this is about best we can do. Okay, now I got another example. Last example of this section. It wants you to find the vertical and horizontal asymptotes, find the intervals of increase, decrease, find the local mins, maximums, find the intervals of concavity and the inflection points. Lastly, use all of this information to sketch the graph. Okay? So here's our function. F of x is equal to 1 plus 1 over x plus 1 over x squared. Okay, now if you wanted to, you could find a least common denominator and all that, and you'd get x squared plus x plus 1. Now, what we can do with this is we could find the vertical asymptotes, because that's the first thing that they ask us to do. To find the vertical asymptotes of a function, all you have to do, since we got the simplified form, is take the denominator and set it equal to 0. Now this one's really easy. X squared is equal to 0. The only solution is 0. So we've got a vertical asymptote at x equals 0. You could have seen that from here. Like, I can't plug 0, can't plug in 0. Those are the only bad numbers. Okay, now let's find the horizontal asymptotes. Now, you could either do it here or do it here. Remember, to find the horizontal asymptotes, we could take a limit. Take the limit as x goes to infinity. If x goes to infinity, 1 over infinity is 0. 1 over infinity squared is 0. 0 plus 1 is 1. Doing the limit here, remember, you could just look at the coefficients. The 1 and the 1, divide by 1. So we've got a horizontal asymptote at y is equal to 1. Okay, now it wants us to find the intervals of increasing and decreasing. So you could do it one of two ways. You could differentiate this, or you could differentiate this. Here we'd have to use a quotient rule, but the numerator would already be simplified for us. Here we're going to have to do power rules, but then to do the first derivative test, to find the intervals of increasing, decreasing, we're going to have to simplify it as a fraction. I'm going to find the derivative here. F prime of x is equal to, this is going to give you negative x to the negative second minus 2x to the negative third. Okay, I know I did that really quickly. Alright, so let me rewrite this. Negative 1 over x squared minus 2 over x cubed. Let's go ahead and find the least common denominator, which is x cubed, divided by, well, this still needs an x, so it's going to be negative x minus 2. Which, we can factor out that negative. X plus 2, x cubed. Alright, so I'm going to erase all the work that we had to get there. And I don't believe we need the original function. Let's see. Local minimums, maximum values, intervals of concavity, inflection points. Yeah, I don't think we need the original function anymore.